depends if I'm going up first or if I go down and back and across, what would that be? That would be a refrigerator again. You see? Or I could go this way, this way, this way. That's also refrigerator. So I need to go more this way, like clockwise more, to make it a heat engine, right? More clockwise orderly. If I'm going this way, more a refrigerator. So the right-hand rule is coming into this, right? Or I could even change one of the stages. I don't necessarily need to make it always isobaric, isothermal. Maybe, what if I go up? What if I do this kind of stage? Let's start with the same initial conditions. 0.306, and I'm going to start with the same condition, 2.026. How about if I go up like this as an ln function? Some weird behavior. P is proportional to any kind of function, you know. So it could be some variable until you get to 3 times the volume. Then go down isovolumically, and go back isothermally. Or I can go down isovolumically, go back isobarically. As long as it's clockwise, it's a heat engine, right? Like this. So I can go down isovolumically, isobarically, or go down isovolumically and go back isothermally. Let's calculate the efficiency of that. So this one is going to be the same pressure, 0.675. This is isothermal.
Wait, so in this case, work done by gas is the positive value?
It's still positive, yeah.
So can I?
So I still did it this way so that it becomes a heat engine.
Okay, so can I see kind of like the integral of the whole area? So it's like,
Yeah, but if you go this way, it becomes a refrigerator.
it's negative.
It's negative, yeah.
So can I say because it's from a smaller value to bigger value, so the volume of the, the first stage, that's a very big volume right there. It's like, and then like when you go down, the work is 0, and
Yes.
when you go back up,
The work
that's
is
a
negative.
So it's kind of much a bigger area minus the smaller
Yeah,
area.
because going back, this area is negative from here to
Right.
here, but it's less volume than this area, right?
Yes.
The area of this whole thing.
That's right.
So you're subtracting that, yeah, exactly.
So can I see as math? It's kind
Now,
of,
is this one going to be more efficient or less? Well, it looks like it's going to do more work because the area is bigger, right? But I don't know whether it's going to be more efficient or not. You see, efficiency is the ratio of how much heat it takes to run the engine divided by the work that it does over how much heat. So this might require more heat to get it started. You see? But it might still do more work. So we don't know if it's more efficient. And that's the challenge of engineering, is designing cars with good engines where, yeah, it might do more work, but then I want less heat input, for it. So it could be any kind of a function. So first we would need to solve for what variable this has to be. Let's say it's some constant A. What other the variables?
plus B.
Maybe plus B, right? A general ln function. In other words, what do A and B need to be so that the pressure here, right? Because I know P1 is equal to A ln of B1 plus B. So P1 is going to be what? 2.026 times 10 to the 5th. V1 is going to be 0.306 plus B. Right? Oh, it probably needs to tell us what this pressure is then, right? P2. So it needs to give us the behavior of that function and then the two endpoints so that we can solve for what are the general A and B values that can fit through those points, right? So then we can say, okay, let this be 3.0, let's say, times 10 to the fifth. Can we solve for A and B now? Yeah, right, we should be able to solve that. We can subtract this minus this. 3 minus 2.026 times 10 to the fifth, and then this minus this, the b's will cancel. So I get a ln of 0.918 minus a ln of 0.306. Right? Then we can say this is going to be right? Okay, so then we should be able to solve for A. Oh, this was just 3, right? Wasn't this ratio 3? ln of 3, because it was 3 times the volume. So it was just divided by so A has to be that number to make it work, right? Then you can put it back into here and solve for B. Either one of these two equations, right? So then we have, I'll take this value, put it right into here, and then multiply by 0.918 ln. Then add it to that number, plus, so this one came out negative, and when you take it over there, it becomes, then you add it. So then B comes out to be 252,665.66. Okay, so now I have the equation. I can do the work in stage 1, work in stage 2, and all of that, right? So, well, first we can calculate also the temperature at this stage, right? What's the temperature? Just by simply using the ideal gas law, right? If this is given to me, and then this has, we already know the volume, right? And we already know the pressure, so what can we do? P2, V2 is nRT2. So if P2 is 3 times 10 to the fifth, V2 is 0.918, 25 moles, 8.314. We can calculate just T2 from there. So see, you're always going to be using a combination of the ideal gas law, some form of the first law of thermo, plus the work is integral PdV. So now, then put that in this corner, 1,324.99 Kelvin. Right? So then I can do the work in stage 1 is going to be what? The work by the gas in stage 1, integral PdV. Right? But then what's the P function? This general weird function, right? So So A is this number, 553,243.4, ln of D plus, what? B is gonna be that number,
52.
252,665.66 dV from 0.306 to 0.918. What's the integral of ln of V? Well, we could just put that in solver and have the TI integrated. We don't have to worry about it. Okay, so now integral. Put that into your integral function. In the TI-89, it's F3, right? Integral 553. 243. 4.
Excellent.
The integral's coming out negative.
Yeah.
Wait, how could that be? How could that come out negative? It should come out positive, huh? That's bizarre. How could that come out negative? 553.
Oh. Okay, so I can see that since it's 0.306 to 0.918, which is less than 1. So ln for the domain from less than 1, it gives you a negative value. So since A is greater than B, about 2 times, so you multiply it by a negative value, that gives a very, very long range. Just see that? It's below x-axis, so that's why it gives you a negative value.
Yeah,
So
but
the model is kind of wrong.
the model is wrong, huh?
Yeah, you
But
should
even
say,
though we solve for A and B, it's still wrong, huh?
let's not put A right there.
Well, what if we put A inside of the ln of AV?
ln of AB.
And then A could be a certain factor.
Oh, that's right. Yeah,
Would that work better?
Yeah, I feel like that would.
Yeah, so in other words, if we're mathematically modeling it as an ln, it has to also fit the criteria of that
Yeah.
function, Possibly, yeah, you're right. P is ln of AV. Well, that just means it's just ln of A. That's not gonna help us, because isn't that the same as ln of A plus ln of B?
Yeah.
And then ln of A is just under the
Just
constant.
shift. Yeah, you just shift it.
Oh, God. just adds another constant here.
Yeah.
Hmm. Didn't work. Okay, maybe does the ln doesn't work, huh? ln of b to the, I'm thinking ln of b to the power a, but then that's the same as doing a
Times.
times that, so that doesn't change.
Ideally, you can change the interval of volume, like from 1 to,
What?
they change the volume.
Oh, don't make it 0.306.
Yeah, make another number.
Oh, just make it a
Greater
number
than-
more than 1.
Yeah, greater than 1.
Oh. That's weird. It's funny. Okay, well, let's just change the function something else, something like pressure is a
Square root
square
of
root of the,
plus
then, yeah, plus b, right? That work? Something that looks like that. Let's see if that works. So this is a good exercise in trying to understand the nature of the log function. So square root of b plus b, so then you're gonna say 2.026 times 10 to the fifth equals a square root of 0.306 plus b, then 3 times 10 to the fifth, a square root of 0.918 plus b. Then you're gonna subtract them. 3 minus 2.026 times 10 to the fifth. Subtract this minus this, so I'm gonna get square root of 0.918 minus square root of 0.306. Okay, so then that's gonna be so A is gonna come out. Then I put that into here. So for B, then put that into this function. Please don't come out negative. I don't think this one will. Okay, it worked out. W1 is 156.44 kilojoules. Okay. So then delta E1 is going to be 3 halves NR NR delta T, right? So, but now delta T is larger because T2 is 1,324.99 minus the original temperature, which was 298.15, right? Delta E is 320, W1 is 156, and then Q1 is going to be the sum of that, right? This plus that. How about Q2? Q2 is going to be delta E2, right? Q2 is going to be delta E2, and then W2 is going to be 0. So that's still isovolumic, right? So then what's the delta E2 going to be? Same as delta E1, right? Because you're going back down to the same temperature of, yeah, it's going to go back down. So it's going to be the same as this guy. So negative 320.14. And then W2 is 0. And then Q3 is going to be the same as before. I didn't change anything for that portion, right? Q3, whatever it was, I don't remember. W3, whatever it was, I don't remember. And delta E3, whatever it was, I don't remember. So now if I'm trying to calculate the efficiency, what do I do? Because I'm kind of interested in that the most. It's going to be the total work done by this gas, which is going to be what? This one, 156.44 minus, right? The work done when we were going back. So what was the answer for that? The W3.
68.08.
Okay. 68.01. So it's going to do more work, right? But then how much heat did it take to get it going? 476, right? Okay, now let's see if it's more efficient or not. Ooh, slightly more efficient, not too much. Right? So it did a lot more work, but it took more heat to get it done. Okay? So this also illustrates to you an example of some general case where it's not isovolumic or isothermal, something random. Okay, cool. So we're ready then for Monday to start a adiabatic process and talking about monatomic versus diatomic versus polyatomic, all that stuff. Chapter 21.